Hey y'all, welcome back to another round of Greg's ranting. Oh, Robison rants. I like that. Welcome back to another round of Robison rants. And yeah, let's keep going. So last time we talked about this idea of Taylor expansions. Expansion. And in particular, we were interested in these nice functions, e to the x, sine of x, and cosine of x. Okay. Now, today I would like to use the idea of the complex number or the imaginary number j. And we're going to look at the relationship that occurs when I take j, which is defined as -1, and start applying it to e to the x and see what pops out. Okay? So this will be probably a fairly short video, but this is the idea that we're after. So here it is. Ready? What happens when I consider e to the j times, I'll just put x in here. Okay. So go ahead for a moment. Perform a Taylor expansion on this function. You got it? Good, 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 good. Well, let's go ahead and use the right side of the screen here. And what do we have? Remember a Taylor expansion, and we'll do it for x naught equals 0. A Taylor expansion says we need to evaluate the function at x naught. Okay, that's the first step. So if we evaluate e to the j at x equals 0, I get 1. Okay, good so far? All right. So the next step, well, let's see. I have to take a derivative of my function and evaluate at x0. Okay. So let's go ahead and do that. Now, of course, the derivative of e to the jx, if I take a spatial derivative of this, okay, j is a constant. It's a number, doesn't vary. And so what I end up with is j times e to the jx. Right? So here, when I evaluate it, I have j e to the j times 0. And so I get just j. Well, how about f double prime of x naught? Yeah. So now I have j squared e to the j times 0. And hopefully you see it. I get a -1, which is kind of goofy. And keep going. If I do an f triple prime of x naught, I get j cubed e to the j times 0 equals -j. Oh, that's so cool. Okay, right? You see it. So at the end of the day, if I would like to write out an expression for e to the jx, right? What do I get? I get 1 plus j times x over 1 factorial, right? The first derivative evaluated at x naught times x over 1 factorial. Then I have plus the second derivative evaluated at x naught times x squared over 2 factorial plus the third derivative evaluated at x naught times x to the third over 3 factorial. Hopefully you see the pattern, right? Plus the fourth derivative over 4 factorial, right? Hopefully you see it, plus the fifth derivative over 5 factorial plus, yeah. Okay. Cool so far? Okay, good. Now you see it's kind of weird that every once in a while, once you get j squared, you end up with a real number again, -1. And when you do j to the fourth, you end up with +1, right? J squared is -1. J squared is the square root of -1 squared, which is equal to -1. And of course, j to the fourth equals -1. I'll put it squared times -1 squared. Well, that's just -1 times -1, which is equal to 1. So that's kind of cool, is that every once in a while you end up with a real number again, even when you're using the imaginary numbers. But wait, there's more. Oh, this is so cool. Yeah. You ready for it? Let's group terms of j and the real numbers. So take the real terms and put them in one grouping. Take the terms that involve j and put them in another grouping. You ready for it? So here we go. So we notice that 1 is real, has no j, so we'll put 1. We'll start off with 1. And then we notice, okay, the next term has a j in it, so we're not interested. The next term, okay, I have -x squared over 2 factorial. Okay, and the next term, oh, that has a j in it, but the next term doesn't. So I have a plus x to the fourth over 4 factorial. And you can probably already see the pattern here. What's the next term going to be? Yeah. You're going to get a minus x to the sixth over 6 factorial. Okay, good. And I'll put plus ... Okay. Well, how about the terms that just involve j? Okay, so I'll put a plus in here, and I'll put the j. So I'll pull that common term of j out. Well, let's take a look. This one doesn't have a j. We've already accounted for that. That's here, so we don't need to worry about that. We've taken care of these terms. Well, how about this term? Okay, well, I've got a j, and it's just times x. How about the fourth term? Yeah, you see it's minus x cubed over 3 factorial. And the next one that involves a j, I get plus x to the fifth over 5 factorial. And what's the next one going to be? Yeah. Minus x to the seventh over 7 factorial. And then I'll put plus ... You getting excited yet? Yeah. Where have you seen this? Let's look at this. Let's take a look at the first term. Where have you seen this before? Good. That is the Taylor expansion for cosine. Right? Go back and look at the last lecture, or go back and look at your notes. This is the Taylor expansion for the cosine function. And where have you seen this before? Yeah, it is, put the j in there, That is the Taylor expansion of the sine function. Yeah, it turns out that e to the imaginary number times x is equal to cosine of x plus the imaginary number times sine of x. This is known as Euler's relation. And you will want to have this in your memory banks. This is so stinking important. Have it memorized. You want to have Euler's relation memorized. It helps out. It comes up so often. It's so helpful. You don't want to have to look it up. Okay? Okay. Now, this also is helpful. Let me give you some ideas. Having Euler's relation, so e to the jx equals cosine of x plus j sine of x. Okay. This is really helpful, for example, in expressing sines and cosines as well. Consider for a moment, what is e to the negative j times x? Yeah, hopefully you see, well, okay, anywhere where I see an x, I should put in a negative x. So I could write this. Right? All I've done between these two is I've taken x and I've replaced it with negative x. But cosine is an even function, which means I can rewrite this as cosine of x. And sine is an odd function, which means I can rewrite it as negative j sine of x. Okay. So that's also a really helpful thing to remember. Now here's the second relationship that's very nice to have. Imagine for a second that I add these two together. In other words, I take e to the jx plus e to the negative jx. What is that going to be equal to? Good. Hopefully you see it. 2 cosine of x. How about e to the jx minus e to the negative jx? What is that going to be equal to? Yeah, hopefully you see it again. This is going to be 2j, excuse me, swap there, sine of x. Okay. So aside from having Euler's relation under your belt, you might want to remember these two relationships as well. They come in handy. That cosine of x can be written as e to the jx plus e to the negative jx over 2. And that sine of x can be written as e to the jx minus e to the negative jx over 2j. You don't seem that impressed. Huh. Okay. Let me give you a couple of, let's do a couple of examples. Okay. Now, these are completely unrelated to the class in particular, but they're very helpful just in the general knowledge base, just the general sense of doing things. Okay. So let me give you one. This is the one that I can remember off the top of my head. Let's say you need to do something like this. The integral of cosine squared, let's make it interesting. Let's say cosine cubed cosine cubed of x dx. See if you can do Euler's relation to help make this easier. You got it? Yeah, good. Okay. Now, I know that you know some tricks. Okay. You could do something like the cosine of x over 2 must be equal to the cosine squared of, you could say something like the cosine of 2 times x over 2 is equal to the cosine squared of x over 2 minus the sine squared of x over 2. So you could try to do kind of fancy things like this and kind of finagle your way through. Okay? Let's do something different. Okay? I'm going to use Euler's relation. So if I consider this for a second, I could write this as e to the jx plus e to the negative jx cubed over 8. Or if you prefer, 2 cubed. 2 cubed. Okay? Well, now let's go ahead and do this. Let's go ahead and expand out this, FOIL it. And since it's a perfect cube, we can use Pascal's triangle. Okay. In other words, here are the coefficients. And so I could rewrite this, if I wanted, as, let's see, this would be e to the 3jx, right? That first term cubed, and 1 would be the coefficient. Then I would have something like plus 3 e to the 2jx e to the negative jx, right? I take this first term squared, multiply by that, and this is my coefficient. And I keep going. 3e to the jx e to the negative 2jx. And then finally I have plus e to the negative 3jx. All over, I'll leave this in here for right now. Let's keep it as 2, and I'll pull the 1/4 out. Good so far? Well, hopefully you see now. Now look at this. I'm going to combine the cubed one right here. Okay? And I will combine these two. In other words, I'm going to use Euler's relation in reverse. I used Euler's relation to turn cosines into e to the jx's. Now I'm going to go back the other way. So look at this. What does this give me? This gives me the integral, well, e to the 3jx plus e to the negative 3jx over 2. That's just cosine of 3x, right? And then look at this, e to the 2jx, right? And then I have negative jx. I can add the exponents right here. And so I get something that says plus 3 cosine of x dx. Now that hasn't helped us do the integration yet, but I would argue, look at this. We've managed to convert the cosine cubed into a linear combination of cosines. And now we can do our integration. So it turns out we have, okay, so this would be 1/12 sine of 3x plus, let's see here, 3/4 sine of x. and we're done. No? Maybe? I don't know. I think that's a lot easier than doing things like double angle formulas or doing something like, okay, cosine squared of x equals 1 minus sine squared of x. You know, like I think that's a little bit easier. I don't know. Maybe you disagree with me. So there's a couple of things I'll mention. Okay. Notice that because you have the same base, one of the other advantages that comes into play is that when you multiply, when you're squaring something, it makes life easier. You have the same base of this number, so it's easy to convert it. Okay. So just another little thing. So this is a tool that you really need to have in your back pocket. It helps make some of these manipulations involving sines and cosines easier. Cool, huh? Well, we could get really daring. Okay, so I'm really off book here, but we could get daring. Let's go ahead and look at something like, I don't know, what would cosine squared of x times sine of x be? And I'm just making this up off the top of my head. I haven't done this prior. Okay, go ahead, go. Give it a shot. See if you can simplify the integrand using Euler's relation before you do the integral. You got it? Sweet. Well, let's take a gander here. So looking at just the integrand, I have something like e to the jx plus e to the negative jx over 2. And that entire quantity is squared. And I'm multiplying by e to the jx minus e to the jx over 2j. Sorry, that I is going to sneak its way in there. I can feel it. Well, it's not for the faint of heart, that is for say. But I would rather multiply things than have to do a bunch of u subs or trig subs or anything else, if you ask me. So what do I have? I have e to the 2jx plus 2e to the 0. Ooh, that's nice, right? I have jx e to the negative jx, so that's nice. And then I have plus e to the negative 2jx. Okay. And then I have e to the jx minus e to the negative, excuse me, there's a negative sign there, jx. Well, let's see if this helps us out at all. Of course, we have that 1 over 8j floating around out front as well. Well, let's see if this helps us. We're going to have to FOIL this sucker. So e times this, so I get e to the 3jx. And then we notice that this gives me 1. So I have plus 2e to the jx plus now negative jx and positive. So I get an e to the jx. It's always nice. And then we have a couple more. We have plus, now I have this 2jx and negative jx. So I get e to the jx. Excuse me, that's a minus. I dropped the sign. I have a minus 2 e to the negative jx. And then I have minus e to the negative 3jx. And that's 1 over 8j. Well, okay. So, rock and roll. Notice I have jx and jx. I can combine those, which is always nice. So what do I have? I have 1 over 8j, and I have e to the 3jx minus e to the negative 3jx. Okay. And then what else do I have? I have plus 3 e to the jx minus e to the negative jx. So I'll leave that 1/4 in front, that 1/4, and I'll convert this stuff back. So what do I have? I have the integral of sine of 3x plus 3 sine of x dx. And I'll leave it for you from at that point. But hopefully you see that we've managed to convert this sucker, that integrand, using Euler's relation and some algebra into this one. They're perfectly analogous. Now, how would you do that otherwise? Yeah, I mean, there's some trig subs like a 1 minus sine squared equals cosine squared. And then you'd have to distribute it out, and then you'd have to factor somehow that sine cubed. So, yeah, pretty cool, huh? Hey, thanks for your attention. I'll see you next time.